So we can start now. A pleasure to welcome you all to the second talk this week in all of this heat. So we'll keep the windows open. And so Yutaka is going to tell us something about abduction proving in Isabelle. Please take it away.
Yeah, thanks for the introduction. So the slides are available on the tiny URL link. So if you want to go back and if you forgot what I talked in the previous slide, you can follow the link. And yeah, the tool is, and the implementation of the tool is available, and you can find it if you search for data61/PSL on Google or somewhere. And I'm also going to use the full advantage of the screen, and it seems like this part might be hidden, so if you want to see it, just tell me. I'm going to close the door. Okay, so abduction prover in Isabelle HOL. Abduction usually means kidnapping in day-to-day English, right? But in this context, abduction refers to a specific style of reasoning, which I'm going to explain later. So it's going to be a high-level talk, so I skip some technical details which may confuse you, and you can ask questions in that case. And I'm going to talk about the specific implementation, and if you are interested, I can help you installing it later. Okay. So these are the contents of today's talk. First, I'm going to ask some questions about you to check if I prepared slides for the right audience. Then I'm going to introduce myself. Then I show you what Isabelle is if you are not using it. And I want to start the technical part with a demo so that you get to know what it is. Then I'm going to talk about three components: tactic names, prediction, tactic arguments prediction, and auxiliary lemma conjecturing. Okay, let's get started. So first, I want to know who has used OCaml and Haskell or standard email for more than 8 hours in your life. I was expecting 90%, so it seems all right. What about Isabelle, Coke, Lean, Whole, 4, all right? Okay, actually it's higher. No. I was expecting a bit lower. Okay, if I say sledgehammer, who knows what I'm talking about? Okay, it's actually more than I expected. Cool. Okay. Now I know who you are, and let me tell you who I am. So I'm Yutaka. I was born and grew up in Japan, but I always wanted to go abroad. But, you know, it's not that easy if you don't have foreign parents and go to just normal Japanese school. So first, I couldn't study abroad, so I went to India for internship for 8 months. And then I was sort of prepared and went to Germany for my master's degree, where I started using Isabelle. And I wrote a master's thesis about code generation from Isabelle to data parallel Haskell. Then I did what's called pre-PhD. So some people do postdoc, right? Some people do postdoc. And I spent 3 to 4 years in Australia working in a research team known for the SEL for microkernel. But I didn't work on the SEL for microkernel. Instead of that, I worked in a team which was developing a domestic language to build trustworthy file systems. So during this time, I became more interested in PL ideas. And even though my main research is AI for error proving, I sometimes use PL techniques or programming language techniques in my research. So I started my PhD studies in Austria. First, I built a tool to recommend tactic names in Austria. And you know what tactics are, right? And then I moved to Prague and studied how to recommend tactic arguments. Then I did postdoc in Singapore where I worked on evolutionary computation.
That's fine.
That's fine. Okay. Then until 2 or 3 weeks ago, I was working in the UK for a private company. And I worked on the abduction prover, which is gonna be the main part of this talk. So our specific implementation, so I was working for Huawei Technologies Research and Development, but in the UK, but I'm not representing Huawei in this meeting. And fortunately, they allowed us to open source this tool, so it's available publicly at GitHub. So our implementation is specific to Isabelle, but the underlying concept should be transferable to other provers, like Coq, Lin. Yep. So I traveled a lot in my life, which wasn't particularly easy, which is, I think, understandable for most academics. And I learned 3 lessons of life the hard way. First, we know that we have to tolerate imperfect solutions once in a while. And for normal people, it's so obvious, but somehow I noticed that logicians and programming language people tend to find it difficult to tolerate imperfect solutions. But maybe the machine learning revolution might be changing our attitudes. And I also learned that we should fail early if we fail. Usually minor mistakes are okay, as long as we can safeguard ourselves to avoid major failures. But we should also try to notice when things go wrong so that we are not going to waste too much resource. The last thing is that we should sometimes focus on making small, good steps, even though we can't make a big step straight away. And we should try to make sure that the small steps are actually steps forward. And in the rest of the talk, I want to get back to these 3 lessons in a more scientific setting. Okay, let's look at Isabelle. So most of you have used some interactive theorem prover, but maybe not Isabelle. So this is how Isabelle looks like using the standard editor called Genedit. And yeah, probably I don't have to explain function definitions here, right? We are defining 2 reverse functions, and you see type signature and function body. And now we are trying to prove the equivalence of these 2 reverse functions. It's not confusing at all, right? We don't have to explain the type signature for you. Okay, and Isabelle has more than 200 tactics, and since both reverse functions are defined recursively, probably it makes sense to use some sort of proof by induction, right? So I applied the induction tactic in line 14 and with some arguments. So here we said induction on XS while generalizing YS. And in the lower half, you can see that Isabelle, in the output pane, you see that we have a base case and step case. So in the step case, we have an induction hypothesis, and using induction hypothesis, we want to prove the goal. Yep. Fortunately, in this case, when we apply auto, both sub-goals are gone, and yeah.
What's the difference between the 2 symbols? I'm guessing hash is concatenation. What does add stand for?
Hash is actually list constructor, and add is concatenation. Or
Add
append.
is concatenation.
Add is append.
Add is append.
Yeah.
Nice.
Yeah. The exact definition doesn't really matter much in the rest of this talk, to be honest. So yeah, some people haven't heard about sledgehammer, so I'm going to explain it a bit. So sledgehammer is sort of a powerful tool which goes beyond tactic level. So sledgehammer takes proof obligations in higher order logic and translates them into less expressive logics, and it exploits external provers like vampire, sparse, the e-prover to find proofs for the proof obligations in higher order logic originally. But the weakness of sledgehammer is that since it results to less expressive logics, if the problem is inherently higher order logic, like inductive problems, the performance is pretty poor. So if we apply sledgehammer here, after probably 30 seconds, it gives up. But if we do the induction part manually, sledgehammer can find the proof script. Because the remaining part, the base case and the step case, are not like inherently higher order logic. The nature of the problem is not higher order logic. Okay, now I changed the proof obligation a little bit on the right-hand side. And this is actually not even a theorem. We can't prove it because it's false. It's bad. So Isabelle has a tool called quick check. And I think Coke has quick check or something like that, right? Sorry, rock. And it basically tries to find a counterexample to the statement. And in this case, it found a counterexample presented here. So it was a mistake, but we noticed that we made a mistake, so we can avoid wasting time for this problem. So we managed to fail early. Yeah, so that's Isabelle. And I think most provers, interactive provers, are similar in a way. We are users and we have their prover of our choice. We define proof goals in a proof context, which may contain auxiliary definitions and lemmas. And we apply tactics, and tactics return sub-goals. And we keep applying tactics to new sub-goals. And we also have strong tools like sledgehammer. They may give us error messages, which is actually a good thing because we noticed that something went wrong. And we keep applying tactics and tools. And sometimes we have to introduce auxiliary lemmas. We also have counterexample finders like quick check. And we have to keep doing this until we get no sub-goals are left for the final goal. So essentially, the enterprise of finding a proof script boils down to 3 tasks. The first task is to find the right tactic. So in the Isabelle committee, it's called proof methods, but they are basically the same thing. We also have to identify the right arguments we should pass to each tactic. And sometimes we have to come up with auxiliary lemmas. So these are 3 main tasks we have to handle. And proof engineering is notoriously frustrating, and people often get grumpy. That's why I'm using AI to automate the process. So I think so far it's very simple. Do you have questions? Yes.
Just about notation. So if at is concatenation and second definition doesn't contain at, how it could be purely in principle?
Sorry?
Is there any silent assumptions how concatenation is dealt with in a second definition?
So concatenation definition is somewhere above. And if you know the definition of concatenation, you can prove it.
Oh,
Yeah. So I have to put everything. I can't put everything in one slide. Okay, so let me show you my tool, which I introduced for proof automation. Okay, so I pre-recorded the demo. It because it's safer. So and this video is available on YouTube. So this is a program developed at the Chalmers University. It's called TIP, Tons of Inductive Problems. And first we apply sledgehammer to this problem. So it's called problem TIP prop 01, and we apply sledgehammer here. But sledgehammer gave up after 30 seconds. So this is fast forwarded video, so it takes much longer in real time. And sledgehammer gave up because it's inherently higher order problem. So I installed my tool using this import statement here and apply my tool, abduction prover for hammer tool. It took more than 160 seconds and it found this proof script, which we can copy and paste. Sorry?
What kind of proof is it?
It's a proof about natural number. So we move to the next problem about reverse function and the length of the list. Sledgehammer fails again. So we introduce the abduction prover for Isabelle and invoke it. So it took more than 2,000 seconds, but the resulting proof script is pretty large. Let's look at one more problem.
Correct answer.
So you can see that it's calling lots of counterexample finders inside. And this time it took 600 seconds to find this proof script.
That's impossible.
Okay, so that's pre-recorded demo, which is safer for me. And let's go to real demo. So this is actually the same problem, prop 01. I installed my tool, abduction prover here. And yeah, lemma is stated here, and if we type sledgehammer, it's gonna fail after some time, but we know that it's gonna fail. So instead of lemma, we say prove this. Yep, and it's gonna take some time. And we have other problems, so let's say prove this one as well. And maybe other problems here. Prove this one as well. Okay, one more. So let's go one. And now, okay, it's getting busy now.
6 points.
Okay, so let's hope that it's not gonna disturb my PowerPoint. And so it's looking for proof now. And meanwhile, let's study how it works. Okay, so there are 3 problems we have to address, right? We have to find out which tactics we use, or tactic names. For this one, I built a tool called Pamper, Proof Method Recommendation System. And here I'm invoking the tool by typing which underscore method here. As I said, proof tactics and proof methods in Isabelle basically mean tactics. And after a while, it made this recommendation. Okay, the induction tactic didn't come up with the most promising candidate, but Isabelle has more than 200 tactics, and at least it became the fourth. So yeah, you should be happy. And yeah, you might be wondering how it managed to make these recommendations. The tool actually has two phases: the preparation phase and the recommendation phase. In the preparation phase, basically training happens here. We take existing large proof corpora. By default, we take what's called the AFP, the Archival Formal Proofs, which is an online repository for Isabelle proofs. It has like more than 300 contributors, and I took this screenshot a while ago, so probably now the size is larger. But proof corpora are very complex data types, and I didn't want to dump complex data structures into machine learning algorithm directly. So we first applied feature extractor, which basically comprises of 108 assertions. Each assertion asks questions about the invocation of tactic. It asks about tactics and the proof goal and the underlying proof context.
So when you say 108 assertions, what's the form of those assertions?
The type of the assertion is that it's a function. It takes a triple of tactic name, proof goal, and the underlying proof context. And the underlying proof context is actually a massive data structure which contains thousands of definitions, and they are like hierarchically defined definitions. And also we have lots of auxiliary lemmas, thousands of them. And it returns a Boolean value. And we have 108 assertions, each of them returns a Boolean value. So output becomes like this. It's a pair of tactic name tagged with an array of Boolean values. This is a much simpler data structure, which even simple machine learning algorithm can handle. So in my case, I chose to use decision tree construction algorithms because it's easy to implement for me, and it gives us more explainable results, more interpretable. Okay. And in the user time or recommendation phase, users have their own problem, right? So first we apply assertions again to transform again the complex data structure for proof goal into a simple data format of Boolean or vectors, and look up the decision tree and produce recommendations. We did evaluation and wrote a paper which got accepted, and I was happy, but at the bottom of heart, this is recorded, right? I have to choose words carefully. I didn't think that tactic name prediction alone was enough. So it's important, but it's not that important. Okay, so this is a evaluation data. So while conducting evaluation, we had training data and evaluation data, right? And we counted how often each tactic was used. And if you look at the top two, you see that SIP and OUT are used very frequently, and together they account for almost half of total all tactic invocations. So if we recommend auto and simp, like half the time you're correct. So the numbers actually are called coincidence rates. I sort of prefer not to explain this in detail, but you can see that if the number goes to 100, it's better. And the number at the top means like how many recommendations we can make. So we get good numbers for auto and simp. And if you go down this table, you see some tactics which are rarely used. So this one, interrupt underscore classes, was used 193 times, which is about 0.1% of the whole tactic invocations, but it has a very strong footstep. So the feature extractor can extract the essence of a problem, which indicates the use of interclasses. So the results are pretty good, even though it wasn't used very massively. But this tool doesn't recommend tactic arguments, and that was a big problem. Some tactics work well without arguments, but some others don't work well, especially the induction tactic performs pretty badly without having the proper arguments. That's why I worked on tactic arguments. Okay. So in this example we have shown previously, we applied the induction tactic with arguments. And I wanted to get this automatically. And I did it by seeing proof development as an implicit tree search. Yeah, and we also knew that we should apply some sort of induction, even though we are not so sure about how we should apply induction. So often when we write proofs, we have rough ideas about how we should attack proof goals, but we don't know the exact steps. So I made a domestic language called PSL, which stands for Proof Strategy Language. So strategies written in PSL are rough ideas about how to attack proof goals. It doesn't tell how exactly we should write proofs. So in this case, I defined a strategy called DIND, which is a sequential combination of 3 sub-strategies: dynamic induct, auto, and is solved. And we applied this strategy using the keyword find underscore proof. And after some time, it finds this proof script. Basically, it constructs a proof tree implicitly. So first, dynamic induct produces lots of candidate inductions. Maybe the first candidate is just induction, which actually leads to this proof obligation, which is the original goal with some strange assumption. It doesn't help you. So if we apply auto, which is the second sub-strategy, auto does some simplification on the assumption, but we still have a proof goal left. So the final step says it's not solved yet, and it forces backtrack. Maybe the second candidate is induction on excess. Why excess? Because the variable excess appeared in the proof goal. We don't actually know if it's actually a good candidate or not. So let's look at what happens. Okay, this time we got the base case and the step case. Looks more promising, but when we applied auto, it didn't solve the second case, step case. So the final sub-strategy says not solved, so we backtrack. And we keep doing this until we found this combination, which led to these 2 sub-goals, and both of them are solved by auto. And that's how the tool managed to produce this proof script. Yeah, I did this research in 2017. And here, actually, the production of induction tactics is not exhaustive. We might miss some important application of induction, but still there is a higher chance that we can get the right induction. And by checking if it's solved or not, we managed to fail early. Questions so far?
The
One thing that I think is useful is to have access to the proof, no? And as I have some experience with the Sledgehammer, and what disappoints me from social grad of automation is that I cannot use that as a tool for teaching induction, for instance.
Yeah, this is a tool for
It's applied
automation.
automatically, but it's not possible in this abduction approach to expand the proof so that I can show the proof to the students how the inductive scheme is prepared automatically and so on.
So the tool actually produces lots of intermediate position lemmas, and technically it's possible, but probably you don't want to look at them. It's very massive. So this is still like a tree search, and we are gradually moving to graph expansion algorithm. So we covered tactic argument prediction for recommendation, but often we have to make intermediate lemmas. So this is one of the results of our demo. I think the biggest one from probe 6. But if you look at this carefully, most of them are actually auxiliary lemmas, and the last two lemmas are about the final goal. And I think in theory, you could just keep applying tactics forever, but it's just too challenging and readability is gonna be poor. So I would say it's much better to make small steps. In this case, they are auxiliary lemmas. Yeah, so we have to be able to come up with good lemmas. But what do you mean by a good lemma? What makes a lemma a good lemma? And I think there are 3 criteria. The first one is that the lemma shouldn't be false, right? The lemma is false, we can't prove it. The second one is that a lemma should be useful to attack the final goal. The last criterion is that the lemma should be easier than the original goal. Otherwise, there is no point of having a lemma. And conjecture, so coming up with the right lemma is often called conjecturing. And it seems people say that it's an important problem, but challenging one. But I think that coming up with the right or good lemma straight away is not actually necessary if we can fail early. How do we do that? So my idea is to use modus ponens. Does anybody not know modus ponens? It's okay, right? So my idea is to use modus ponens for conjecturing like this. We want to attack the final goal, and we want to get conjecture, and the conjecture should imply goal. Goal might be difficult, so we want to have something easier. And we can apply quick check, and we can try to prove it. If quick check finds no counterexample, maybe it's not obviously false. Maybe quick check is not strong enough, but at least we know that there is no very obvious, it's not obviously false. It might be false though. And if we manage to prove goal by assuming a conjecture, we can be sure that this conjecture is actually a useful one. And we hope that the conjecture is actually easier and by proving it actually. Okay. So my idea is that we can come up with lots of conjectures. Many of them are bad conjectures, but we want to filter out bad ones so that we can focus on good ones. Now I came up with 3 conjectures. Conjecture 1, 2, 3. Maybe for conjecture 1, we can't prove the goal assuming conjecture 1 easily. So conjecture 1 doesn't look like an useful one. So we discard it. Maybe for conjecture 2, quick check finds a counterexample. So we are sort of sure that this is not a good conjecture. For conjecture 3, we managed to prove the goal assuming conjecture 3, and quick check doesn't find a counterexample. So we can hope that conjecture 3 is easier, even though there is actually no guarantee that conjecture 3 is actually easier than the goal itself. Yeah, we have to tolerate the imperfection here. And this style of reasoning is often called abduction, at least by me. And it resembles the style of reasoning done by detectives in detective stories. We have a goal, and we want to come up with a statement that can be used to explain the goal. Okay, that's the approach I took for the abduction prover. So the essence is here. And let's look at this for 5 seconds. 1, 2, 3, 4, 5. Do you think you have seen something similar previously in this slide? Not in this slide, but in this talk. I feel like that this was very similar to this situation when we applied tactics, induction tactic. So we are using modus ponens, right? And I showed the induction tactic, but the induction tactic is actually a bit complicated. So here I'm going to show even a simpler problem, which is true or false. We want to prove that the disjunction of true, false is provable. That's super obvious, right? And first we apply the introduction rule called disjunction introduction 1. And the proof goal becomes disjunction to true. And yeah, it's just true, so we apply true introduction, and this is super simple, we don't have to think about it. But the first step is actually a bit interesting. Let's look at it. This is the disjunction introduction rule 1. It says, if we know x, we know that x or y. Not surprising, right? Yeah. And we applied the introduction tactic, which comes, and we pass disjunction introduction 1 as an argument. So we ended up having this situation here. We had a original goal, and we transformed the original goal to sub-goal here. So T stands for 2. And you see the sub-goal here. And yeah, in this case, this one is slightly harder than this one, right? Okay, and what about this implication? The implication part was taken care of by the tactic internally inside Isabelle. So when the tactic transformed this proof obligation to this proof obligation, inside Isabelle, tactic guaranteed this part. So superficially, it looks like the transformation from here to there. So generally speaking, tactic applications can be formulated like this. We have a goal, and we transform goal into sub-goal. And internally, this implication was handled by Isabelle. Now, let's compare tactic application against conjecturing. They are both instances of mode respondence, right? There's no fundamental difference, I think. So they look the same and they are the same, so we should treat them like the same thing. So I syntactic applications as conjecturing steps. So previously I was talking about seeing proof development as tree search. And in this tree, you see that active applications correspond to edges between nodes. And the aim was to find a path from the root node to the leaf node, which represents the proof completion. And the proof script was the path from the root to the leaf node. Now we are saying that active applications are conjecturing. They are the same thing. So we should add conjecturing steps as edges. But when we start thinking about conjecturing as edges in the tree, we notice that often we use the same conjecture or auxiliary lemma for many proof obligations. For example, if you define an algebraic data structure and operations on it, and if you want to prove some properties, maybe you need commutativity, and probably there are lots of problems which require commutativity. So in terms of graphical representations, it corresponds to that situation where lots of nodes point to a lemma that describes commutativity. But this is not a tree anymore, right? It's a graph. So we are sort of shifting the understanding of proof development from tree search to graph expansion. Yeah. And now the aim is to find a portion of the graph that represents the whole proof script. Question: Do you think this graph should be acyclic, or this can be cyclic graph? Raise your hand if this can be acyclic. One. Raise your hand if this graph shouldn't be acyclic.
Maybe you have to say a little bit more. You have to say a little bit more about the meaning of the arrows.
Yeah, good point. So here, goal points to lemma C, right? Which means final goal. We can prove final goal using lemma C. And actually, it depends on the concrete implementation, I guess. But from what I have observed, it's better to have this as a acyclic graph. And I think for people who said this shouldn't be acyclic, we're thinking that we shouldn't have a cyclic arguments, right?
Maybe we could have something like co-induction.
I didn't think about co-induction. Anyway, so that's what the idea of having graph structure as the basis of proof development. And let's hope that my tool actually worked. Okay, so this is plot 1. We look at the output pane, and you see that it's testing conjectures. So this corresponds to the quick check invocation. So we keep applying quick check, and yeah, we got this proof script, which I should be able to copy and paste with one click. So you see that we proved this final goal. So the final goal was like this one, right? And it appears here. We have to change the name of variables somehow. And the final goal was proved using sometimes tactics, but we also used conjectures. And here, I think I used conjecturing as a tactic application as conjecturing. Another example, so we have proof invocation here, and if we go down deep, we find this proof script, which we can copy and paste. And it's a massive proof script, but this is actually a portion of the graph, and all the lemmas appearing in these proof scripts are used. Yeah. And proposition 11, 8 to 600 seconds, and we got this proof script. Oh. Okay, so this is the biggest proof script we produced from TIP06. And okay, maybe I can zoom in. I can't zoom. Yes, some conjectures are produced based on template. And some conjectures are produced by mutating the current proof obligation. And sometimes multiple conjectures are produced at once. And we are always using modus ponens. For example, this is the final goal. And we used two auxiliary lemmas to attack the final goal. And to prove the auxiliary lemmas, we introduced two auxiliary lemmas. So here, we introduced these auxiliary lemmas. And to prove these auxiliary lemmas, we introduced in total 4 auxiliary lemmas. And they are defined here. And to prove them, we introduced 4 more auxiliary lemmas. And here it's a bit interesting because both lemmas use this one. So this lemma is pointed by this node and this node, which means it's more than 3, it's actually a graph here. Yeah. And we keep doing this. And now this lemma is already proved because it was used previously. So we actually have multiple nodes pointing to the same auxiliary lemma from different levels. Because now we are talking about graphs instead of trees. Yeah. So I talked about how to address these 3 tasks using 3 lessons. I avoided technical details, but to implement this tool, actually we have to take up more technical challenges. I focused on the major part. Yeah, that's it.